Hello, in this video I'm going to be talking about adiabatic compression on an ideal gas. And so again, I'm writing down the ideal gas equation because we will need it in the future. And I just want to remind you all that this is the ideal gas equation and we will always be working with it. So, basically, what we're going to look at is what is an adiabatic process. Well, adiabatic means that no heat flows in this compression. So like how in the isothermal compression, the temperature did not change and we held that as constant. Well, in this one, we're going to have no heat flowing through this system. So it's the opposite of a isothermal basically, because in this one, the temperature does change, and in this one, instead of a slow compression like the isothermal, it's a faster compression that we use. And so let's just remind us also of the first law of thermodynamics. Delta U equals Q plus W. But in this instance, Q is 0 because we're saying no heat is going to flow. So the change in internal energy is going to be just the work done to the system. That's it. Pretty simple. And now we're going to use something called the Equi-Partition Theorem. Now the Equi-Partition Theorem basically says that the internal energy of a system is equal to 1/2 times the degrees of freedom of the system times nk T. This is a pretty important theorem. And so F as in the number of degrees of freedom. So a system in 3 dimensions can move left, right, up, down, and forward and backwards. And that's 3 degrees of freedom right there. But we're going to keep it generalized for now. And so now we relate the two. So what we need to do first is take the derivative of this. du equals 1/2 F N K dt. Now remember, we're saying the temperature is changing in this. So that's why it's dt here. So now we take this to be du equals the work done. So what we're going to say is, well, and also, well, what we first need to do is relate this to the ideal gas law, which we definitely can do. It's right here. And we see this here. So minus P dV equals 1/2 F N K dt. This PVT comes from here. We can see here, all that comes in together. And now we just solve this differential equation. But you gotta also remember from the ideal gas law, P equals NKT over V. And we substitute that in to here. So we end up with, well, I'll just write it out. Minus NKT for V dV equals 1/2 F N K dt. And this is really useful. Now we can cancel things out. We have a dV over V, we have a dt. We need to divide that t over. This cancels this out. And so what we're left with is 1/2 F 1 over T dt equals minus 1 over v dv. I just kind of flipped the sides here. I know this is a simple differential equation with the variables already separated. So we can just integrate now. Integrate both sides. And we end up with, we did this integral last time, so I'm just going to skip through it. We end up with 1/2 f natural log t final over t initial equals, I'm just writing it on the line below because I'm running out of room, natural log v final over v initial. And if you don't understand that integral, I did it in the last video. So check that out, and I'm just going to move forward. But this is pretty interesting here. Not only because what we see here is 1/2 f is just a constant, we can also expand this, raise each to the exponential power, and then just rewrite it. So it actually ends up being v final t final to the 1/2 equals v initial t initial to the 1/2. And this equation makes a little more sense to me, so I'm going to stop here for a little bit, because to me, looking at this makes more sense than the other equation that most books use. So what this says is you can find any starting point of your system and the final volume of a system, and you can find the final temperature of it. You can algebraically solve for it. And so that's really useful, because we're used to having a starting point and say we know how much we want to compress it because this system is being compressed rapidly. That's the action we're doing to it. And we can determine what the final volume is going to be already. And then we can find the final temperature of what it'll be. So this is the most useful part of it. Other textbooks actually write this as Vt to the 1/2 equals a constant. So basically what this is saying is that any point of volume and temperature on the curve will be constant. And what that curve basically is what I'll show you as an adiabatic Pv diagram. I'm going to write it to the side over here. So you have P and V. And first I'm going to write two isothermals right here. So isothermal 1, isothermal 2. Because we're changing temperature, and isothermals are constant temperature. So what our adiabatic is going to look like is going from this temperature at this final volume to this temperature at this final volume. It's going to look like this exponential sort of right here. And we're compressing, so it's going this way. So that's what the PV diagram looks like. It goes between two temperatures, and it's being compressed or expanded. Either way, just reverses the flow. And that's basically it. That's what the PV diagram looks like. Pretty simple once you think about it. And now, one other way you'll see this written in textbooks is V to the gamma times P equals a constant. And what this gamma factor is F plus 2 divided by F. Now this comes in handy when you're working in terms of gamma. Gamma will show up later, and gamma is entirely based on the degrees of freedom of the system. But if you're just solving problems and working with isothermal expansions, I think this equation is the easiest to understand and the easiest to use. And that's it. Thank you for watching.